Yeah, so thank you, Roland. Welcome, everybody. It's nice to be here again in this somewhat deviant setting. I have to say I'm home alone except for my dog. My dog sometimes barks, so I hope it will be. I hope it will primarily bark in the Bayesian part of the lecture. Anyway, so I'm going to share my screen, I think. And for that, I need a permission to share the screen. Yeah, so I was certainly dissatisfied with the methodology, and as EJ was. And of course, that's not a sign of weakness of the methodology in itself, of course. I mean, we are always dissatisfied. If we were not dissatisfied, we wouldn't be doing anything. We would just be complacent and sit on our mountain of methods and be happy. But of course, that's not how we are. We always want to go ahead. So that's the fundamental thing. So what I want to do today is give you an overview. I assume you can also see my screen.
Yes.
About I want to give you an overview of the use of frequentist statistics, and I want to make the point that statistics basically is a toolbox, and there's different kinds of toolboxes, and you got frequentist tools, you got Bayesian tools, and you shouldn't be too heavy on that. But of course, yeah, I'm going to argue that the frequentist tools has some very desirable characteristics that the Bayesian tools don't have. And the basis of our discussion today is about, I think, at the core, it's about what is probability and how do we use probability in scientific research. And frequentism, the basis of frequentism, is a very, very simple idea. It's beautifully simple. But it's an idea that people didn't have for most of history. It's only a couple of 100 years old. And the idea is that probability has lawful characteristics if it's understood as a relative frequency with which an event occurs in a long run. So the prototypical example is you throw coins, and the probability of heads, what does that mean? It means the relative frequency with which the coin will fall hands if the experiment is repeated. And the beautiful thing is that if you do this and you you repeat the experiment and you keep on recording the number of heads you've thrown, the relative frequency of heads, that has lawful behavior. It's a lawful kind of randomness, and we use that lawfulness in scientific research. Now, I personally think that this idea that probability is a relative frequency is one of the great ideas of humankind. I mean, you have the sunflowers of Van Gogh, you have the fugues of Bach, and you have the frequentist definition of probability. It's really one of the very beautiful things. And even if you thought it should be not used in scientific research, EJ, it's still a very beautiful idea. How do we use this? And that's often forgotten. And especially in the Bayesian arguments, I think this is something that is not well addressed. We don't ban probability from research, we use it. And we use it in a very definite way, namely by bringing probability into the research design. And the person who first clearly saw how that had to be done is Ronald Fisher, who you see here, an otherwise obnoxious fellow, by the way, not a nice man at all, but a genius. And he had the fantastic idea that if you want to protect your research from all kinds of systematic biases, you shouldn't try to weigh all these biases and make them evenly spaced across conditions. No, you should just have random assignment. Just let the coin decide who gets to into what experimental condition. Or the other fundamental random process in science is random sampling, which means you let chance choose, you draw a coin, you draw a straw, which people are in your sample. And so what's really important is that frequentist statistics and everything what I'm going to say next follows directly from the fact that you use the coin to set up your research. And that means that your research has long-run behavior that can be derived from the long-run behavior of the coin. That's amazing, by the way. It's amazing. So, for instance, if you use random sampling, not if you don't use random sampling, but if you use random sampling, then you know what the sampling distribution of your statistic is. So for instance, you have a group of people, the Dutch population, you draw a random sample of people and test them for corona. You can imagine doing that repeatedly, draw 100 people, draw 100 people again and again and again and again. And each time you tabulate the probability of corona, you know what the distribution of this statistic is going to be. So you know the amount of uncertainty that is going to be present in your sample, in your sampling sample value of the statistic. And also the other very important thing is that you can get definite statements of what would happen if your hypothesis were true. So if the hypothesis were true that 10% of the people actually has corona, that's and something that could function as a null hypothesis, then the probability of, say, finding more than 50 in my sample of 100, if I do this repeatedly, has a definite value, and I can compute that, and it's a real value, an objective value. It's a fact. It's a matter of fact that if I repeat this experiment repeatedly and I have random sampling, this will be the long-run behavior of the statistic. So if my calculation says, if 10% of the people has corona, then the probability of finding 50 or more in your sample is, say, 1 in a million, then that's what it is. If you did it indefinitely often, and that was a true hypothesis, then this is you would find 1 in a million cases. So that's real. It's a fact. It is a objective statement about the research design as it functions in the long run. And that's basically, I could stop here actually, because this is basically the machine. This is the engine of frequentist inference. And actually, I think it's also the engine of a lot of Bayesian inference, which basically uses all of this and then puts a little bit of cream on top. But EJ will of course, counter that. So this is a very powerful weapon. It's not an opinion. Right, so the p-value or that's not an opinion. It's not the degree to which anybody should believe anything. It doesn't have any intrinsic normative value, right? So it doesn't mean you should believe something or not. It is a fact. It's a piece of information about your data in relation to the design. And in that sense, frequentism is objective. Not in other senses, of course. Of course, I mean, there's a lot of choices in your research design that reflect your own opinion on how things should be done. That's not what I'm saying. It's not that there is no subjectivity in scientific research. That would, of course, be an idiotic, stupid idea. But in this particular part, it's not subjective. So why is this such a powerful idea? Well, because you know what your statistic is going to do in the long run, you can control the long-run probability, the long-run frequency of type 1 and type 2 errors. So of incorrectly rejecting your null hypothesis or failing to reject the null hypothesis when it's false. And if you use, it's a really beautiful thing, right? I mean, this is really amazing. If you use a standard, simple, run-of-the-mill null hypothesis test, as you've clicked it in SPSS, if you do that, and you have a real random sampling design, or you have a real random assignment, and the null hypothesis is true, then you know, as a matter of fact, that you will make at most 5% type 1 errors in the long run. I think that's a fantastic piece of information. So I think any statistical method that cannot tell you anything about what your error control is would require some work. The null hypothesis test, this kind of test, so you have an hypothesis, you compute the p-value of these or more extreme deviations from the value under the null, and you say you decide at alpha is 0.05 when the p-value is smaller than 0.05 to reject the null hypothesis, then you know that you will make type 1 errors in 5% of the cases at most. And the great thing about this is that null hypothesis tests can be constructed for almost every research design. So frequentist statistics is for a large part sort of finished. For most normal research designs, you can run a null hypothesis test, and that's also really nice. Whatever your hypothesis is, whatever your design is, whether you are doing mean differences or interaction effects, or you're comparing probabilities or whatever, the p-value is always the same thing. It always has the same interpretation if the null hypothesis were true. And I did this experiment indefinitely often with random sampling or random assignment, then in 5% I would get a value that's this high, or that's as high as the p-value, in p% of the cases I would get the value, this deviation or a larger deviation. So this is really cool, right? So whatever else you want of a statistical method, if you didn't have this, you'd want it, right? So it's like, yeah, it's like, water. You want water in your life. If you don't have water, you die. Okay, so that's okay. Coke is also nice. Coca-Cola is also nice, and beer is nice, and that's all nice. But you want water. This is really a sine qua non for scientific research. So just a little bit about what the p-value does and does not do. So what exactly does a p-value do? Well, in my view, but this is my personal view, so this is it's an answer to the skeptic's argument. So Mary says, well, I did an intervention and I found an effect. And so the intervention is effective because I observed that the experimental condition was doing better than the control condition. And then somebody else says, well, I think that's just a coincidence. Then Mary says, well, okay, so you think it's a coincidence. I think it's a real effect. Well, let's suppose that you are right. Okay, suppose that it was all coincidence and there's no effect. Well, then the probability of observing this or a larger difference in means, for instance, would be 0.01. So you would find this one in so many cases. Okay, so if we repeat the experiment and the null hypothesis were true, then in 1% of the cases we would find this large deviation or a larger one. Yeah, that's it. And that's it. Is that the end of everything? Does world peace ensue? Right? Should I get open the champagne? No, of course not. Have I proven that the effect exists? No, of course not. We're not going to be naive about this, right? It's statistics. Of course you could be wrong. But you have an important piece of information because you know what the probability of your finding or a more extreme one would be if the skeptic were right. Now, the p-value is the probability of data or of a deviation or a larger deviation in the data, given that the hypotheses were true. It's not the probability or 1 minus the probability that the null hypothesis is true. This is really important. It's also not, some people think, oh, maybe in some cases it's almost that. No, it's not that. Right, so I think it's Roeland's example. If you're given that your head is bitten off by a shark, the probability of being dead is pretty high. But given that you're dead, the probability that you were decapitated by a shark is very low, right? So the probability of A given B is not the probability of B given A. That's really important. And it's also not somehow reflected to that. So I don't worry about this. I don't actually think that the probability of hypotheses exists, because I think that hypotheses are either true or false, right? So there's no long run sense in which hypotheses are true or false. So you can say, well, you can of course say, what's the probability that the theory of evolution is true? Right? And it sounds as if you're asking something deep, but you're not asking anything actually. There is no probability of the theory of evolution being true. It's not true today and false tomorrow and then has a long run behavior. No, it's either true or it's false, and we don't know whether it is true or false, but we make our best guess based on the data. Right. So EJ and the other Bayesians, of course, claim that you can actually get the probability of hypotheses from the data by a pretty straightforward application of a very old theorem by Bayes. The inverse probability can be drawn from, if you basically multiply the probability of the data given the hypothesis with the probability of the hypothesis. So you have to put in something there, and that's called the prior probability for the hypothesis. Now, this is not a frequentist, it's not a real probability. It is a degree of belief, or something your gut feeling about whether the hypothesis is true or not. And then outcomes, also not a real probability, but the gut feeling that you ought to have once you've seen the data. So something like the degree of belief you have to attach to the hypothesis once you've seen the data. Now, this is obviously something that frequentism doesn't give you. But I am very, very skeptical about whether Bayesian statistics actually gives you this. I would agree that the posterior probability, so that's the thing on the left, the probability of H given the hypothesis given the data, has some evidential import. I wouldn't be against reporting it, but I think you have to be very gullible to believe that your degrees of belief can be sort of steered by this simple formula. But maybe EJ can this year finally convince me. I don't believe actually that. I think that the Bayesian technique is actually often sold as something that can do magic. It can just do magic. You put the data in and out comes this desired thing, the probability that the hypothesis is true. I don't buy that. I think that that's actually the problem of statistics in psychology. People are treating statistics as a religion, as a sort of magic thing that does the thinking for you. And I don't believe that any statistical method can do that. So I think frequentism offers you a set of tools. And that's what statistical methods are. And tools ought to be used wisely, not rationally. Rationality is a fool's errand. Wisely, it has to be used wisely in view of how the research is set up. So frequentist tools are limited, yes, absolutely. There's a lot of misinterpretation of the p-value, absolutely. That's absolutely true. Bayesian tools are also limited. They have their own problems, and maybe EJ can tell us a little bit about that next. I would say that we just use these tools as we see fit. And I would say that the frequentist tools are essential and the Bayesian tools are added. They are